Hey guys, today we're going to start a new unit on vibrations, waves, and sound. It covers two chapters, chapters 25 and 26 in our book. And the study guide is posted in the Google Classroom. This is the stuff we're going to look at today. So we're going to look at the introduction here. What is a wave? Why are we interested in this stuff? We're going to learn some wave terms, and there's a lot of them. So you're probably going to have to pause this frequently so you can write this stuff down. Because you are going to want to take notes on this because this is just vocabulary so you understand what we're talking about moving forward. And finally, we'll finish up with the wave equation, which is one that we'll be seeing in this unit and in the next one as well. It's a simple equation, but it's one that we'll see a lot. So first off, what is a wave? Up to this point, we have been dealing with moving objects. So you throw a ball up in the air and it hits something and it transfers energy to it. That's mechanics. Now we're moving on to a different type of physics, which is about waves. And with waves, the energy itself moves from place to place. So if I have a rope and I flick the end of the rope, a wave will travel down that rope and shake the hand of the person who's holding the other end of the rope. But I'm not throwing the rope at them to transfer energy to them. I'm just making a wave which travels down the rope. And when that wave reaches their hand, it shakes their hand. But the rope itself pretty much has stayed in one place. Okay, and that's the general idea with waves. It is energy in motion rather than matter in motion. So with a wave, energy moves from place to place, but the medium does not. Now, what is a medium? That's our first vocabulary word. The medium is the material that carries the wave. So I just talked about a rope. If a wave is traveling down a rope, well, the wave is the wave, but the rope is the medium, because if there's no rope, there's no wave in the rope. Another example would be sound. You probably know that sound is a wave. So you can hear my voice right now because my vocal cords are shaking the air and sending waves of energy through the air, which shake the microphone. And then through the miracle of electronics, it shakes your speaker. It shakes the little metal diaphragm in your speaker, which shakes the air and creates waves in the air, which come to your ear and shake the ear. Okay, so the waves are traveling from place to place, from my vocal cords to the microphone and from the speaker to your ear. But the air itself is not moving. I'm not like blowing on the speaker and moving air from my lungs to the speaker to make that noise. Likewise, the speaker in your computer is not blowing a stream of air at you to hit your eardrum and make it move. It's the waves traveling through the air which are hitting your eardrum. But while the air itself stays relatively stationary. Another third example of this is if you see a piece of floating wood in the water. As waves travel through the water, the piece of wood moves up and down, but it doesn't surf along with the waves. Okay, most things in the water just stay where they are as the waves pass underneath them and through them. So the energy moves from place to place, but the medium does not. Okay, that's what is wave. Now we got some terms here. We're going to envision a wave traveling down a rope or down a string. So this straight line here represents the rope, and when I jiggle the rope, then the wave starts traveling along. And I'm going to make some copies of this. So basically, we're imagining a train of waves which are propagating from our left to our right across the page. Okay, let's start off with the one that students have the most trouble with, and that is the term amplitude. Let's move this aside, amplitude, okay? Amplitude, I'm going to put it in here first, is the height of the wave, or I'm going to be more precise with that, the displacement of the wave from the neutral position to the extreme. So see, I have two little green lines here, one right where the rope normally is, and one right on the crest. And the amplitude is the distance from that neutral position to the crest, to the very top here. Since I've mentioned the word crest, I may as well put that in there as well. Okay. The crests are the peaks of the waves, the highest point, the maximum displacement. That really is the best way to describe it. It's the maximum displacement of the medium as the wave passes. Okay, and back to the amplitude again, because that's where I started with this. The amplitude is the distance from the neutral position to the crest. Okay, So it's not from this low point up to the crest, it's from the neutral position to the crest. Now, what about those low points? Those low points should have a name too, and those are called the troughs, okay? Like the trough in when you're plowing a field, or a water trough that animals drink out of, it's a low point. So these lowest points are called the troughs, while the peaks, the high points, are called the crests. Now, the crests and the troughs are the most extreme motion of the medium, and the amplitude is from the neutral position to one of those extremes. So the amplitude could also be the distance from a trough to the neutral position. That would also be the amplitude, okay? Now, the common error that students make is they think that the amplitude is from the trough to the crest, and it's not. Amplitude is from the neutral position to the crest, or from the neutral position to a trough, either one of those. Draw a picture of this. It's easier to remember this stuff if you write them down. Okay, I'm going to drag all this down a little bit. Okay, the next term we have is wavelength. Okay, the wavelength, here we go. Let's do it this way. That'll work. Actually, you know what? I'll put it over here so it's slightly less cluttered. Okay, so the wavelength is the distance in the medium that it takes for one full cycle of the wave. Okay, so here I have it labeled from the waveform passing through the neutral position, coming down, and then it comes up, and then it passes down again, and that's the wavelength. It's a little easier to see wavelength as the distance between two crests. So it is from here to here, that crest. I'm actually going to put another little black mark there, okay? Okay, that's the wavelength from crest to crest. But the wavelength could also be from trough to trough, right? And as I showed the first time, it's from where the waveform passes down through the neutral position to where it passes down through the neutral position again. I'm pointing this out because students sometimes think that the wavelength is from here to here or from here to here. It's not. It's a full cycle. So from crest to crest, that's a full wavelength. Right now we have wavelength is pretty fundamental to wave, so we have an abbreviation for it, which is this Greek letter lambda. It looks like kind of an upside down cursive Y. That is a Greek letter lambda, and that is our symbol for wavelength because it comes up so often. Okay, so that's what we got here. Crests, troughs, what the amplitude is, and what the wavelength is. And of these, the one that students have the most trouble with is the amplitude. Okay, moving along here. Now we're going to get to period versus frequency. Last thing we have is the wave equation. This is where we put all this stuff together. You know what? I'm just going to do this on the paper. That's going to be the easiest way to do it. So I'm going to introduce this all on the paper as if this was a smartboard. Okay, I think we're set. Yeah, that's good enough. Okay, wave equation. Right here it is. V equals lambda F. You'll probably want to pause this and write it down because I have to go fast so I can fit it into the 15 minutes. Okay. V is the speed of the wave. Lambda, we've seen before, that's the wavelength. Wavelength. And we normally measure that in meters. And that is going to be a meter for an individual cycle in the wave. Okay. We saw that on the first one where we had the the squiggly line back and forth, and from crest to crest was wavelength. Well, that is the meters to complete one full cycle in the wave. I have room up here like this. This is the wave. This was the wavelength from crest to crest, or from trough to trough, whatever. But if we measure that in meters, then we have the meters for a given cycle. So that's why the wavelength is in meters per cycle. F is the frequency. We've seen that one before. Okay, and that is in, as you remember, cycles per second. Cycles per second. Now, as you can see, we have meters per cycle and cycles per second. So mathematically, the cycles cancel out, and that leaves us with meters per second. So the wave speed will come out to be meters per second. All right? So V equals lambda F. Very fundamental equation. We're going to be using it a lot in this unit and the next because it deals with the speed of waves, the characteristic of waves. Now, this one here is frequency. It is not period. Okay, so this means that you have to be paying attention to the information that's given to you in a problem or the information that you gather in a lab to see if you are gathering information for the period or for the frequency. And if the number you have is for the period, then you have to flip it upside down so that it is frequency so that you can feed this equation. That's why we care very much about the difference between period and frequency. Because to feed the wave equation, we got to have frequency. Okay, now here's a useful number for you. The speed of sound equals 340 meters per second on a normal day. So suppose that we have the speed of the wave is 340 meters per second because that's the speed of sound. Say that we have a frequency of, let's say, 170 hertz. 170 cycles per second. Okay, that's 170 cycles per second. The question is, what's the wavelength? Find lambda. And the way we do this is we just plug the numbers that we've got into this equation. Now we know that 340 meters per second is equal to lambda times 170 cycles per second, right? We want to solve for lambda, so we're going to divide both sides by 170 cycles per second. 170 cycles per second. Whoops, I did that upside down. 170 cycles per second. Okay, 340 divided by 170, that's going to be 2. Right? The seconds cancel and we get meters per cycle in my messy writing here, but we're running out of time. That's why I'm doing it this way. Okay, so we divided 340 by 170, we got 2. So lambda equals 2 meters per cycle. Okay, we can work this backwards. If we're given the wavelength and the frequency, given the wavelength and the frequency, we can find the speed of the wave. If we're given the speed of the wave and the wavelength, we can find the frequency. So we should be able to do all those. There are examples in your book, and you'll have some practice on the worksheet that you do. Okay, thank you for your time. We will see you next time.